Good morning, grade 9. Hope you are all doing well and being safe. This is Miss Pamela giving the physics course. Today we are going to start with chapter 6, section 1, which talks about work. So please open your books on page 189 and follow up with me. What is work? Work is done when a force is applied to an object and the object moves in the direction of the applied force. So in order to do work, we need to apply force on an object and the object must move due to the applied force. If you look at the figure in front of you to the left, a person is pushing a wall, and the wall does not move, of course, due to this person's force. So this person is not doing any work. Now look at the figure to the right. A person is pulling and pushing a desk, and the desk moves due to his applied force. Since he is applying a force and the object is moving due to his force, then he is doing work. Calculating work. Work is calculated by multiplying the force applied on an object by the distance that the object moves. Force and displacement are in the same direction. So in this simple equation, the force is in the same direction as the displacement. We will consider other cases later in this lesson. So in this case, or in this equation, the force and displacement have the same direction. This is why we can calculate work by multiplying the force applied on an object by the displacement of this object. So the distance that the object moves due to this force. Work is measured in a unit called joules. Force is measured in newtons, of course, and distance is in meters. So as we already stated, work is when we apply force on an object. So we do work when we apply force on an object and the object moves due to this force. So if the object does not move, we are not doing work. And in order to calculate work, if the force and the displacement are in the same direction, we multiply the force applied on the object by the displacement of that object due to this force. By rearrangement of this simple equation, we can calculate the force applied on an object if we know the work that is done and the displacement of the object using the first equation we see in front of us. F is equal to work over displacement. And we can also know the displacement of the object if we know the work that is done and the applied force. By using the second equation that we see in front of us, displacement is equal to work over the applied force. Work is measured in joules, force in newtons, and distance in meters. We already said that the unit of work is joules, so work is measured in joules. What is a joule? A joule is a small unit. You do a joule of work when you lift a medium-sized apple through a height of 1 meter. The table below provides some examples of typical amounts of work. So look at the table in front of you. If you want to melt an ice cube, the work that is required to melt this ice cube is 10 to the power 4 joules. In order to light a 100-watt bulb for 1 minute, we need 6,000 joules of work. A human heartbeat requires 0.5 joules of work. So these are several examples in order to make the unit joules clear for you. Example: an intern pushes a 72-kilogram patient on a 15-kilogram gurney, producing an acceleration of 0.6 meters per second squared. How much work does the intern do by pushing the patient and the gurney through a distance of 2.5 meters? Assume that the gurney moves without friction. First, we write the given. So the mass is equal to the mass of the patient and the mass of the gurney. So we combine them together because the intern pushes them both together. So 72 plus 15 is equal to 87 kilograms. The distance that the gurney and the patient moves is equal to 2.5 meter, and the acceleration of the gurney and the patient is equal to 0.6 meter per second squared. They need us to find work. In order to find work, since the force and displacement are in the same direction in this example, we use the equation that we stated in the slides before. So work is equal to force times displacement. Displacement is given, 2.5 meters, but the force is not given. We need to find it. We already know, using Newton's second law of motion, that the force acting on an object that is accelerating is equal to the mass of this object times the acceleration of the object. So the force acting on the gurney and the patient is equal to 87 kilograms, which is the mass of the gurney and the patient combined, times 0.6 meter per second squared. So the force is equal to 52 newtons. Now we can calculate the work being done. Work is equal to force times displacement equal to 52 newtons times 2.5 meters, and the answer is 130 joules. Since we already stated that work is equal to force times displacement if force and displacement are in the same direction. How do we calculate work if force and displacement are not in the same direction? So if the force exerted on an object is at an angle with the displacement of the object, then only the component of the force in the direction of the displacement does work. So we only consider the component of the force in the direction of the displacement. So in this case, if the force and displacement are at an angle to each other and not in the same direction, we use the equation that we see in front of us. Work is equal to force measured in newtons times displacement or distance measured in meters, the distance that the object moves, times cosine angle. Angle is the angle between force and displacement, and it's measured in degrees. So here we consider the angle between the force and displacement, and we use this equation so we can only consider the component of the force that is in the direction of the displacement. Now look at the figure in front of you. This is an example where the force acting on an object and the displacement of the object are not in the same direction. They have an angle between them. So here in this example, the force that is being exerted by the person on the carriage is equal to 15 newtons, and the displacement of the object is equal to 30 meters, and the direction or the angle between the displacement and the force is equal to 30 degrees. In this case, in order to calculate work, we cannot just multiply force and distance. We only need to consider the component of the force that is in the same direction as the displacement. So we calculate force times the displacement times cosine angle. And here the angle is the angle between the force and the displacement. So 15 newtons times 30 meters times cosine 30 degrees, and it will be equal to 1299.03 joules. By rearrangement of this equation, we can calculate the force acting on an object if we know the angle between the force and the displacement and the work being done and the displacement of the object. Using the first equation we see in front of us, force is equal to work over displacement times cosine angle. We can also calculate the displacement if we know the work being done and the force applied on the object and the angle between the force and the displacement. Using the second equation, displacement is equal to work over force times cosine angle. Work is measured in joules, force in newtons, distance in meters, and the angle between force and displacement is measured in degrees. The work that is done on an object may be positive, zero, or negative, depending on the angle between the force and the displacement. So whenever the force and the displacement are not in the same direction, the work that is done may be positive, zero, or negative. It is positive if the angle is less than 90 degrees. If the angle between the force that is applied and the displacement of the object is less than 90 degrees, then the work is positive, as you see in the figure in front of you to the left. In the middle, they are telling us if the angle is 90 degrees, so if the displacement and the force are perpendicular to each other, then the work that is done is zero. And if the angle is greater than 90 degrees, then the work that is done is less than zero, so it is negative. Here we must note that the work done by a force is equal to zero in two cases, not only if the force is perpendicular to the direction of motion as we stated in the previous slide, but also if force is exerted and there is no motion. So if we exert force on an object and the object does not move, then our work is zero. And if we exert force on an object that is perpendicular to the direction of the motion of the object, then also the work that is done is zero. Note, if an object is accelerating, then the force applied to the object is equal to mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meter per second squared. So, if you need to know the work that is done on an object that is accelerating, you need to know the force. To calculate the force, you use Newton's second law by multiplying the mass of the object by the acceleration of the object if the object is accelerating. Also, if you need to know the work done by gravity, or you need to know the work of a person that is carrying an object opposite to gravity, like in the figure you see in front of you to the right, you calculate force by multiplying mass times g, which is the acceleration due to gravity, which is usually 9.8 unless it is stated otherwise. So if they ask you to find the force, the work done by gravity, or the work done by a person that is carrying anything upwards opposite to the force of gravity, you calculate force by multiplying mass times g. As a homework, please solve numbers 2 and 3, page 191, number 5, page 193, and numbers 12 and 14, page 196. Your homeworks must be done and submitted to me on Tuesday, April 28th. Good luck, thank you, and stay safe.